Welcome to the deep dive. Today, we're plunging into a topic that's really reshaping how we interact with technology, with information, large language models, LLMs. Chances are you interact with them all the time, maybe without even, fully realizing it. But how do these systems actually work? How do they seem to think?
It's a huge question.
It is. So our mission on this deep dive is to pull back the curtain a bit on LLMs, using the insights from the sources you've shared. We want to unpack the core tech, understand how these complex systems are built, and maybe even find some surprising limitations.
Absolutely. And it's a field moving incredibly fast, so getting a grip on these foundational bits is, it's crucial. You need it to understand the capabilities and the current boundaries.
Right.
And what's really striking is that pretty much at the heart of all modern LLMs, you find this one revolutionary architecture, the transformer model. It basically changed the whole game for language AI.
Okay, transformer model. Let's start with something maybe more familiar. You know when your phone suggests the next word as you type?
Yeah, text prediction.
Exactly. LLMs do something kind of similar, predicting words, but the difference in scale and sophistication, it's huge,
Yes.
right? So what's the big leap?
That's a great way to put it, because the core distinction is key. Those phone predictors, they're usually pretty simple models, very limited context, maybe just the last couple of words.
Like, I'm going to the work, and it says store.
Precisely. Quick, basic, useful for texting. But LLMs, things like GPT-4, they're playing a whole different sport. They're built on these advanced transformer models trained on, vast data sets.
Unimaginably vast, probably.
Oh, yeah. And this lets them understand and generate really complex, nuanced text over long, long passages. So for that same start, I'm going to the essay. An LLM might understand the context of your whole conversation and suggest something like museum to see the new art exhibit.
Wow. That shows a richness, a context awareness the simple ones just don't have.
Exactly. That's the difference.
So what was the tech breakthrough? What allowed for that jump?
That really comes down to a team at Google Brain. Their 2017 paper, it had that famous title, Attention is All You Need. It just completely revolutionized NLP, natural language processing.
Attention is all you need. I remember that making waves.
It did. They introduced this key mechanism called self-attention. Now, instead of processing words one by one, sequentially, like older models did, imagine you could just glance at a whole paragraph and instantly grasp how every word relates to every other word, regardless of how far apart they are. That's kind of what self-attention lets the transformer do. It allows the model to weigh the importance of each word relative to all the others all at once in parallel.
So it captures context much better.
And faster.
Much better and much faster because of that parallel processing. It's brilliant at handling what we call long-range dependencies. Meaning connecting related words even if they're far apart in the text. Like imagine a long text about Napoleon Bonaparte, discusses his life, battles. Then way later it says his campaigns reshaped Europe.
Right. An older model might forget who his refers to. Exactly. Or if it said, the Battle of Waterloo was in 1815, that date marked a turning point. A transformer easily links that date back to 1815 and his back to Napoleon, even across many sentences. It's this ability that underpins models like GPT-4.
So, okay, the big picture here is we've moved from just guessing the next word to something much closer to, understanding complex language, like across whole documents.
That's a good way to think about it, yeah, a major leap in comprehension.
So we have this amazing architecture, the transformer. Genius stuff. But how do you actually, build one of these things? It's not just flicking a switch, right? It sounds like a huge engineering effort.
Oh, absolutely. It's a massive undertaking. It really breaks down into two main stages, and it starts with just a staggering amount of data.
Okay, stage one?
Stage one is pre-training. This is where the model gets its basic education, its foundational knowledge of language. Picture just immense amounts of text data.
Like the whole internet.
Pretty much. Billions of web pages, books, articles, code. Basically, a huge chunk of all the text humanity has produced. This data gets fed into these super powerful computers, GPUs, graphics processing units.
Right, not just your standard processor.
No, these are specialized for this kind of work. They're equipped with billions of these things called parameters. Think of them as adjustable knobs, like weights and biases.
Okay.
And during pre-training, the model is constantly adjusting these knobs, figuring out patterns, relationships, the structure of language. It's like beating the brain's basic wiring.
And this takes?
Weeks, sometimes months. And it requires enormous amounts of computational power, which is, frankly, very expensive.
I bet.
The end result of all this is what we call the base model. Now, it's really important to get this. This base model isn't what you usually interact with, like when you chat with ChatGPT.
Right, you mentioned that. It's
Yeah.
raw.
Exactly. It's the raw intelligence. It contains all the learned tokens, the basic units of language it understands, like words, parts of words, punctuation. It's incredibly knowledgeable, but not yet helpful, you know?
And this is the P and T in GPT, pre-trained transformer.
Precisely. Generative pre-trained transformer. That first phase gives you the P and T. The G, generative, comes from its ability to produce text.
Okay, so you've got this massive, raw base model brain. It knows language, but it's not necessarily useful yet. How do you turn it into something helpful, something that can actually answer my questions properly?
That brings us to stage 2, fine-tuning. This is where you take that broad knowledge from the base model and you refine it, you specialize it for specific tasks.
Like making it good at conversation.
Exactly. If you want a chatbot, you fine-tune it using data that consists of good conversations, questions and answers, instructions and responses. This data set is much smaller than the pre-training data, but it's highly curated, very specific to the desired skill.
So you're adjusting those same knobs, the parameters again.
Yes, but this time you're adjusting them based on this task-specific data. The goal is to make the model better at the specific thing you want it to do, be helpful, follow instructions, maintain a certain tone, whatever the application requires. It shapes the raw intelligence into something practical.
Okay, that makes sense. But how do you know if the fine-tuning actually, well, worked? How do you check if it's behaving the way you want?
That's a crucial part of the fine-tuning process itself, evaluation. You have teams of people, human evaluators, who interact with the model during fine-tuning.
So real people are chatting with it.
Essentially, yes. They ask it questions, give it prompts, test its limits. They're carefully looking at how the model responds. Is it accurate? Is it helpful? Is it safe? Is it following the instructions correctly? Is it exhibiting the desired behavior?
And if it's not?
Then adjustments are made. It's an iterative loop. Evaluate. Adjust the fine-tuning data or process. Evaluate again. This goes on until the model consistently performs well according to the criteria. And the outcome of all this refinement, this human-guided shaping, is what we call the assistant model. That's the polished, helpful, instruction-following model that you typically interact with.
So the base model has the raw knowledge, but the assistant model knows how to use that knowledge effectively for us. Let's really hammer that home, the difference between that raw base model and the polished assistant model you end up chatting with. It sounds like a night and day difference in practice.
Oh, it absolutely is. And the sources we looked at give a really clear picture of this. If you were to interact directly with a raw base model, yes, it can predict the next word, the next token, grammatically correctly. But its response to a question might be, well, unhelpful. It might just continue your sentence statistically or give a generic, unfocused answer that doesn't actually address what you asked. It's not really trying to be helpful. It's just completing a pattern. It has the knowledge, but not the alignment, not the instruction-following ability.
Like someone who crammed for a test but doesn't actually understand the subject?
That's a pretty good analogy, actually. Whereas the assistant model, because it's gone through that intensive fine-tuning and evaluation with human feedback, it's much more intelligent in the way we perceive it. It understands the intent behind your question and tries to give you the helpful, relevant output you're looking for.
Right.
That fine-tuning step is absolutely crucial for making these things useful in the real world. It bridges the gap between raw prediction and genuine assistance. If you've ever played with some early, unaligned models online, you'll know exactly what I mean. The difference is stark.
It really highlights the importance of that human element in the training loop. You know, for something that sounds a bit weird, honestly, this reversal curse, what on earth is that?
Yeah, it is a bit counterintuitive, isn't it? The reversal curse points to this surprising limitation, a specific failure of generalization in LLMs. Basically, here's the problem.
Yeah.
You train an LLM explicitly on a fact like A is B.
Okay, like Paris is the capital of France.
Yes.
A is B.
Exactly. So the model sees lots of examples like that. But then, surprisingly, if you ask it the reverse question, what is the capital of France, which is like asking what is B, the model struggles. It doesn't automatically infer that the answer is Paris or A.
Really? Even if it was trained on Paris is the capital of France?
That's the curse. It might not reliably give you the right answer. And the really weird part, according to the research, is that the chance of it getting the right answer, Paris, isn't significantly higher than it just picking some other random city name it knows.
That seems fundamentally wrong somehow. If you know A is B, surely you know B is A. How can it not get that? Is it a flaw in the training data or something deeper?
It's definitely strange from a human perspective, and that's why researchers are digging into it. Now, there's a nuance here. It gets interesting.
Okay.
If the model sees that A is B relationship within a larger piece of text, like embedded in a paragraph discussing French geography, it often can figure out the reverse relationship when prompted later in that context.
Ah, so context helps.
Context helps in that specific instance, but the ability doesn't seem to generalize well to standalone, direct questions asked later, based only on having learned A is B facts in isolation during training.
So how did researchers prove this wasn't just a fluke?
They did experiments. They fine-tuned models, like versions of GPT-3 and Llama, on completely made-up facts. For example, they'd train it on Uriah Hawthorne as the composer of Abyssal Melodies. A is B.
A fictional person in composition. Got it.
Right. Then they'd ask the model who composed Abyssal Melodies, and consistently the models failed to answer Uriah Hawthorne. They couldn't reverse the learned association.
Wow.
And this seems to hold true across different sizes of models, different families of models, and just adding more A is B data doesn't fix it. It's even observable in very advanced models like ChatGPT, GPT 3.5, even GPT-4.
So even the big ones have this issue.
Yes. They might handle real-world facts okay, like the Paris example, probably because they've seen Paris is the capital of France, and the capital of France is Paris countless times in their massive training data. But if they've primarily learned a relationship in only one direction, A is B, they struggle with the reverse, B is A, especially for less common or the fictional facts used in testing.
That is truly fascinating. It really underscores that these models, despite being incredibly powerful pattern matchers, don't necessarily understand concepts like symmetry or reciprocity in the same intuitive way a human does. They learn the patterns they're shown.
Exactly. It shows a specific way their learning mechanism works and highlights that there's still these, well, surprising blind spots.
What an incredible journey we've taken today. We kicked off with the transformer model, that huge leap forward, getting us from simple word guessing to understanding complex language.
The attention is all you need. Revolution.
Right. Then we walked through the massive effort of building these models, the huge pre-training phase to build that base knowledge,
Pouring in unbelievable amounts of text data.
and then the crucial fine-tuning step, guided by humans, to shape that raw power into the useful assistant models we actually talk to.
Turning knowledge into helpfulness.
And finally, we bumped into this really curious limitation, the reversal curse, showing that even these advanced systems don't always learn or generalize in ways we might intuitively expect.
Yeah, it's a great summary. This whole deep dive really illuminates the amazing progress, but also, the subtle challenges and the frontiers where research is still pushing. It's clearly not just about predicting the next word anymore. It's about how context, training data, and these specific learning patterns shape both the intelligence and the limitations.
Absolutely. That reversal curse is a perfect example. It reminds us that as these LMs get woven more deeply into everything we do, really understanding how they learn, and crucially what their built-in limitations might be, is becoming more and more vital.
I couldn't agree more.
So here's something to think about. What questions does something like the reversal curse raise for you about how we design AI, how we test it, and ultimately how much we trust it, especially when dealing with information where that kind of relational understanding is critical, something to ponder.